Welcome to this medal lecture to be given by Michel as a recipient of the Cassini Award, which is one of the 4 union awards or medals that are being awarded every year by the EDU. So this is the highest recognition that you can receive from the EDU. And with the medal in bronze with the face of Cassini, there also comes an honorary membership of the EDU. So we are very proud of our union awardees, and I'm looking very much forward to this medal lecture. There's a very nice tradition that we hear about the career and the science of our union awardees at these lectures. So Michel Mayor is awarded the Cassini Medal and the honorary membership for his major discoveries in the field of exoplanets, and that's both regarding observations and theory, and through detection methods and instrument developments in this rapidly developing new domain of modern astrophysics. So I'm looking very much forward to learn about what is actually the content of this science. I'm not in the same subject, so to me it's a great opportunity to hear about these things. And I want to congratulate Michel Mayor once again with the Cassini Medal.
Thank you very much, Mr. President.
You're not allowed to speak here. No, he told us yesterday. Okay, so and after this little intermezzo, we can get to the science, please.
Thank you. So, ladies and gentlemen, my lecture will be a mix between some very general presentation of the field of extrasolar planet and with a little bit more specialized aspect related to the detection of Earth-type planet, because evidently on the long term we always have the dream to find some place for potential life development. How many planets do we have here? This is a very small part in the center of the Milky Way. The Milky Way, something like few 100 billion of stars, plus minus similar to the Sun. So this is a very old question. Already more than 2,000 years ago, people was dreaming of what is called at the time the plurality of worlds in the universe, or maybe later in the same letter from Epicurus, the possibility of some of this world could be inhabited. So the modern terminology, do we have planets? And maybe planetary systems. It's very strange. Everybody believes that astronomers was absolutely convinced that we should have a lot of planetary systems in the universe. In fact, it was not the case. If you are looking here, the estimated number of planetary systems in the Milky Way versus the epoch of these publications, and it's a very big name of astronomy, Sir Jeans, in Cambridge, Chaplin, Harvard, and so on. So you see that until 1943, in fact, everybody believed that we do not have other planetary systems in the Milky Way apart the solar system. And these were based on a wrong hypothesis. It's the problem everybody knew that we need to have a nebula. From Laplace, Kant, that we need to have a nebula around the star to form the planet. But we do not have any correct theory to explain the formation of such a nebula around stars. The classical theory proposed by Sir Jeans was the cross encounter. Oh, sorry, a cross encounter. So, but the probability to have two stars crossing very close together is so small that the probability to such an event is almost zero. So, no way to produce planetary nebula like this. So, and the things change dramatically in the 40s. With a jump by a factor of 10 to the 9 or something like this. And you see in astronomy, you are not afraid to change your ideas. You have Russell, and you have Russell here. So, in fact, and today, the observations are really at the level here. It depends if you count the number of planetary systems or the number of planets, because you can have several planets. So, the first approximation that almost every star should have planetary system. I like very much this picture. This picture was obtained by the Hubble Space Telescope 21 years ago. They looked with the telescope, the Orion Nebulae, looking few young stars in front of the nebula, born in the last few million years. So few million years compared to the 4 billion years of the solar system, they are really young stars. And you see, all of them, or most of them, have a small disk of matter surrounding these young stars. And the reason is simply because during the collapse of the cloud, you have always turbulence and excess of angular momentum, and so you have always some gas and dust orbiting the star and forming this kind of structure. And this is the nebula supposed to be the nursery to form planetary system. And so from, okay, we already have some hints of the existence of this accretion disk before. For example, you have excess in the infrared on the spectra of stars. So, but I believe this was absolutely explicit. And if the physics is able to produce some planet here, it's some kind of microscopic start procedure. In fact, we don't have any reason to believe that it's not a very general phenomena. And a priori, we can imagine that we should have a huge proportion of stars with planetary system. Nevertheless, it's not so easy to detect them, because the contrast of luminosity between the star and the planet is so dramatic. In the solar system, it's a factor 10 to the 9 between the Sun and Jupiter. Jupiter, the largest one, is reflecting only a very teeny fraction of the luminosity of the Sun. So the direct observation is very, very difficult. So we have to find some indirect way to detect this planet. I will go back to... So if you have a planet, we cannot see the planet. Here is a star. As the ratio of the mass between the star and the planet is very huge, so the star is doing a very small wobble around the gravity center of the system. And if you do the spectrum of the star, you can observe a small Doppler shift, periodic Doppler shift, due to the gravitational influence of the star. All these things are extremely small, so we need to be extremely efficient in the way to analyze the photons, because all the Doppler information is distributed on the full domain of wavelengths. You have, I don't know, several thousands or dozens of thousands of atomic lines in the spectrum, so you have to find some way to concentrate the Doppler information to get the velocity of the star. And this was a technical trick we used to measure precisely the velocity. It's called a cross-correlation technique. It's some way to concentrate all the Doppler information on one quantity, it's the velocity. So we used this technique. We developed a new spectrograph with French colleague in Haute-Provence a little bit more than 20 years ago. The spectrograph is linked with the fiber optics to the focus of the Cassegrain focus of this old telescope here. This telescope is 2 meters size. It's not very original. It's not a modern telescope, but this is not so important. What was important is the spectrograph. And we were expecting to find long period giant planet first. And it was a very strange thing that after only a few months, we discovered here a very strange object. Here you have the velocity measured by the star versus the time, in fact, the phase. In fact, you see you have this periodic change of the velocity, and this indicates that an object like a mass with a mass of about half the mass of Jupiter, in a period only of 4 days, is orbiting the star. And evidently, nobody was expecting to find a Jupiter-sized planet orbiting a star with a period so short, with so short period. And this was a priori opposite to the theory, because to form a giant planet, you need to agglomerate ice particles. And ice particles exist evidently only at remote distance of the star. So you cannot expect to have a planet with a short period. So we have apparently a conflict between the paradigm of this time and the observation. And soon the answer came. And in fact, it already exists in the literature by a very nice paper by Peter Goldreich and Scott Tremaine 15 years before, but nobody read carefully the literature. And if this is simulation, if you have a disk of dust and gas, you have a young planet form having attracted all the matter in the torus here, and evidently the influence, the gravitational influence of the planet will react and forms as excess at the resonance in the disk, and then after this excess of matter will react on the motion of the planet. If you are doing correctly the calculation, in fact, you can see that you have a spiraling of this planet. So everything is fine. We can keep the classical theory of the agglomeration of ice and dust particles to form planets. Evidently, we can understand in a simple way this phenomena, but the detail is quite complicated. I will jump now by about 20 years. This is a view of the interferometer set on the Altiplano at 5,000 meters north of Chile. You have 60 dishes, 12 meters of diameter, observing at the same time the same object in the universe, and with the possibility to pack the set of antenna on a few hundred meters, or you can distribute them to something like 14 kilometers to increase the resolution power. So this is working in sub-millimeter wavelengths or millimetric wavelengths, so typically to analyze the cold gas in the universe. It could be formation of galaxies, formation of stars, formation of planets. And this is, maybe we have to, it's good to mention it's a combined effort of Europe, US, and Japan. So 2 years ago, some colleagues decide to use all the set of antenna to observe a small cloud, much smaller than the Orion Nebula, and where we knew that we have some young stars formed in that place. And this is low resolution, it's a classical normal picture. And when you use the interferometer, you can see this. So you have the young stars, the T2 stars, HL2 here. You have another one here. And this is a view produced by the interferometer. The interpretation is absolutely not completely clear, but nevertheless, the most probable thing is that you have the formation of several planets in the disk of this young star. So you see, today we start to have the tools to analyze the sites of formation of planetary system. Okay, first things, we have if you are looking at the very highlights of the last 20 years, the first was the discovery of the orbital migration. Planets are not today at the place where they are born. The second point was what I call the diversity. Here you have a plot where you have the orbital eccentricity versus the semi-major axis. The Earth will be with an almost circular orbit at 1 AU here. Jupiter will be on an almost circular orbit at 5 AU here. And all the big planets of the solar system are almost distributed on such a line. And you see the planets we have discovered on the last 20 years are distributed with a huge scatter of eccentricity, with some incredible example with eccentricity as large as 0.93. So you see this kind of orbit, something like this. So probably we are missing something in the different physical process to explain the formation of planetary system. And once again, you have 51 peg could be in some place here, but you see that you have a lot of system with extremely small period, and for them it's almost circular orbit because of tidal dissipation. And we have accumulated a lot of things. Very high occurrence rate, mass distribution with object with the Earth mass or very large mass, 20 times the mass of Jupiter. Period as short as 0.3 days. Let's imagine a period, a planet orbiting so close, and so on. So we have accumulated a lot of information on the last 20 years. And this explains that the formation mechanism of planetary system are quite complicated. So I will give few hints of what I am more directly involved. It's, we have built and developed a new spectrograph to measure precisely the Doppler velocity. It's a vacuum spectrograph. It's a very thermal control enclosure at a few millikelvin during the night and so on, because you need an incredible stability to find planet on several years or so. And we have been granted by a huge amount of nights. Altogether, I don't know, it's equivalent to 2 years, but spread over 10 years or something like this, on a 3.6 meter telescope in Chile. So the idea was to have some kind of systematic survey of stars and to try to do some statistic of the kind of planet you can find orbiting solar-type stars. So very soon we start to discover a very strange object. And for example, you have this object here, discovered about 2009, with, you see that 4 days, 9 days, 20 days. And the mass are 4 times the mass of the Earth, 7 and 10. You do not have any similar things in the solar system. You don't have what is called super-Earth object between 1 and 10 times the mass of the Earth. And they are extremely packed. These planets are very, very compact in the solar system. And you see this is a typical plot here you have the velocity versus time. Every red spot is a point corresponds to one observation. And if you have one planet, the velocity of the star will change something like this. If you have 2 planets, it will be something like this. If you have 3 planets, evidently, it's more complicated. It's a curve like this, and you need to have the help of a computer to find the solution. So this is, I would say, the first typical example of this very strange compact system with super-Earth. This is another example with 7 planets. Okay, you cannot see. Okay, if you have only the red point, you can see maybe you have something like this. But if you look carefully, in fact, you have several planets. Again, with several planets very packed, 1 day, 5 days, 16 days, and so on, and also relatively low mass objects. And eventually, you immediately start to say, are you sure that such a system are stable? is stable, because if they are so close together, you can suppose that you have some kind of gravitational secular instability. And in fact, it is not. This calculation was done by Jacques Lascar and colleagues in Paris, and you have, if you have one yellow dot every 50,000 years, okay, you feel, and this is for the external planet, this for another planet, and so on and so on, one color by planet, and you see that, okay, you have some perturbation, but on the long term, the system is stable, but it's not so evident, because if you use Newtonian dynamics, it will be unstable. But if you take into account the gravitation, the general relativity correction for the closest one, it helps. But you need also to introduce the problem of tidal dissipation. And it's only when you have all these things together, you can stabilize the system on the long term. So this is typical of the object we are observing, but a huge number of objects like this have been observed. So just a quick look. This is a diagram with the mass, log scale of the period, and evidently the low mass objects are the most difficult to detect. But you see that they are the most numerous. In the volume limited sample we have, you have this huge amount of super Earths we have discovered. In fact, the giant planets are not so frequent. The short period massive planets are extremely rare. For example, the object like 51 Peg, the first one, it's about 1% or something like this. It's very exceptional. So this is typically the kind of survey. If you are looking only at the object with a mass between 3 and 100 times the mass of the Earth, and period less than 1 year, you have already half of the stars with planetary system. Evidently, if you suppose that you have low mass object with relatively long period, we do not have the sensitivity to detect this object. Evidently, we can raise this value to maybe some 100% or close. Okay. Here, if you are looking the frequency, the occurrence as for the very short object, in fact, you have a very drastic rise of the probability to have low mass object orbiting stars. And here you have the same, is the fraction of stars with planet on close orbit as function of the mass between 1 and 3, 3 and 10, and so on. This is a US survey done at Keck telescope, and you see we have the same kind of feature. So we are expecting many low mass planets, rocky planets. Here is just to illustrate one additional constraint we can derive from this survey. This is the relative occurrence or frequency of planetary system as function of the metallicity of stars. If you are at 0, it's a log scale, this will correspond to the sun metallicity. 0.3 will be twice larger, or minus 0.3 it's half the metallicity of the sun. So you see that for the most metallic system, star, in fact, we have maybe 1 star over 4 with a giant planet. And if you are considering only the low mass object, low mass planet, we do not have absolutely the same curve. So we already start to have some constraint coming from the chemical composition of the star for the formation of planetary system. So immediately after the first detections, we add a very nice additional possibility. If you have so many short period objects, in fact, you have a good chance that the orbital plane is such that you have the crossing of the planet in front of the disk. Obviously, you don't have the resolution power to see this picture. The only things you can detect is a small periodic drop of the luminosity due to some kind of eclipse we are using transit. So this technique called the planetary transit gives access to the radius. Doppler measurement give access to the mass, so you have access to the bulk density of the planet, so you start to have some hints of the internal composition of planets. In 1999, we have discovered an object with a period of 3.5 days. So you expect, if the orbital plane is correct, you can dream to have a transit at that phase here. And we gave the information to some colleagues at Boulder with a 10 centimeter. It's not always a big telescope. It's only a 10 centimeter. And exactly at the correct time, few minutes of difference, you have a periodic drop of about 1.5% here. And 7 days after, you have the same drop here, because evidently after 3.5 days, this corresponds to the middle of the afternoon. It was not possible to see it. And so every 7 days, you have this drop here. So the radius corresponds to 1.4 times the radius of Jupiter, the mass 0.7 times the mass of Jupiter. So the mean density, the bulk density, is only 0.3 gram per cubic centimeter. So it's a very low density. This was absolutely direct proof that we have a gaseous giant planet. So here you have the measurement done on the ground with a 10 centimeter telescope. And our colleagues asked the next season sometime on the Hubble Space Telescope. It was not so easy because it's too big telescope for this. It's a very bright star. So they have to be very clever to use correctly this instrument and to build the transit curve from the space. And you see the quality you can have when you are in the space. Evidently, you don't have the trouble of the atmosphere. And immediately, when you have such a beautiful observation here, what you are dreaming. Okay? What could be the smallest planet you can detect by this technique? So, if Jupiter is about 10% of the diameter of the Sun, so the square corresponds to a contrast during the transit of about 1%. If you have the Earth's planet, it should be 10 minus 4. So it starts to be difficult. It's very small. If the transit expected from Jupiter, the Earth is 100 times smaller. So, okay, it's not easy to detect such a drop every year. So 2 satellites have been proposed, one Corot by ESA and French agency, CNES, and it was a very small telescope, and more recently, the NASA very, very important Kepler mission with a diameter of about 1 meter. So the results of the Kepler mission was absolutely dramatic. The idea of such a measurement, of such a mission is absolutely simple. You have a telescope, it orbits around the Earth like this, looking always the same place in the sky, and during several years is doing pictures of the same stars. 100,000 stars, always with the same kind of detectors. Okay, it's not so easy in the reality. And then after you are looking what you have, and you see that several stars have a periodic drop of the luminosity. Several thousand of stars in the field, or a very small field, observed by the Kepler mission, show some periodic drop and indicate the presence of planetary system. Here you have the radius of the detected object versus in unit of Earth radius, and here the logarithmic of the period in days. And you have several colors here. If you have one planetary transit, due to only one planet, it's the black symbols. If you have 3 planets orbiting the same stars, is the blue one. It's this color, it's 5 planets. If it's red, it's 6 planets. So it starts to be absolutely incredible because you have system this indicated immediately that what is equivalent to the ecliptic in the solar system is extremely thin. The scatter of the orbit are at the level of 1 degree. So this kind of packed system are extremely coplanar. But unhappily, the lifetime of this mission was limited, so we do not have accumulated objects. The Earth will be something like here, 1 year, and one radius, Earth radius. So unhappily, we don't have so many objects in the region of the habitability. This is a zoom produced by Battaglia of the radius of the planet observed as a function of the equivalent, the temperature on the surface of the expected for this planet. And you see that you have only planet maybe with 2 or 3 times the mass of the Earth here. The radius 1.5 or something like this. Okay, you have maybe a few objects here, but unhappily, the drawback of this problem is that most of these stars are extremely fine. Typically, the majority are between 13, 14, 15 magnitude. So to get the mass of this object, it's dramatically difficult because we don't have enough photons for that. So it's very difficult. To do some physics, we need to have the mass and the radius. And so, happily, we have another possibility. When you have several planets orbiting the same star, you have some interaction between the different planets, and you have some time variability of the transit. So if you modelize this time variation, you have access to the mass of the planet. It's not so evident. And this is a plot produced by people from the Kepler mission. Here you have the radius, always in terms of Earth radius, as a function of the mass of the planet. And you have, if you are looking only, let's say, the planet with a radius less than 20 times the mass of the Earth, you have a huge scatter. This is a curve expected for Earth-type composition here. And you see you have some object with a radius 4 or 5 times larger, so the density absolutely extremely small. So this is a very big challenge to believe. Is it really rocky planet with a huge atmosphere? What is the physical mechanism to explain such a scatter? So this was the reason why we have built a new spectrograph, because the first one I showed before was in La Silla, in the southern sky, but unhappily, the Kepler targets are all in the northern sky. So this was the reason why we have developed a new instrument to do the follow-up of this kind of observations here. With a 3.5 meter telescope at Canary Island in Spain, and it's almost the same size that we have in the south. This is the same vacuum spectrograph, and we have followed 2 different goals. One is to do the follow-up of the Kepler measurements, with a special goal is to have to put all the observing time to have a significant radius mass diagram for objects with having a low mass, less than 20 times the mass of the Earth. And as we do not have the Kepler target the full night, in fact, we need to have another program, and the second program is to search for very low mass planet in every place of the sun, of the sky, but with, if possible, only at very limited distance. Again, the same diagram we showed before, radius, mass, and the result of our survey. Here, this is the same diagram, radius versus mass. The blue strip here corresponds to a Earth-type composition, so rocky-type planet here. If it was iron pure planet, it will be something like this. If it will be pure water, it will be something like this. And you see, we do not have this kind of an object here. So the only object we have carefully measured, this one, this one, this one, this, and so on, all the objects with radius, with mass less than 6 times the mass of the Earth are really compatible with a rocky composition. And it's only above this limit that we start to have lower density, indicating a huge atmosphere orbiting this, linked to this kind of object. So we will continue. I don't claim at all that this kind of objects do not exist. Maybe they are real, but I can only say that we not have found any of these objects here. So, if you have a good control of the physics, of the formation mechanism, what are the typical phenomena? You have the migration process, I explained before. You have the accretion of the matter to form the planet, and you have the time scale of the disruption of the accretion disk. So if you put everything inside, you can produce this kind of plots. You start with embryos at different distance and so on, and you can use some code for the colors of the core composition. And you see, I will not explain too much this point, this diagram. This is the mass in unit of Earth, but you see that you are expecting some scatter of the composition of the core. A huge difference between the brown and the blue. You see, it's a huge difference of composition for a low mass planet. So this is typically the dialogue we have between theoreticians doing modelization of planetary formation and what we observe with telescopes. What will be the future? Here, this is a US NASA mission expected to be launched in 2017. This is the goal of this mission is to detect orbiting planet, low mass planet, but orbiting bright stars, because this is a difficulty of the Kepler mission. Most of the interesting objects are too faint. And this is the mass versus the radius, always the same diagram. And this is what is called the habitable zone, where you have liquid water expected to the surface of the planet. You have the solar system planet here, with the Earth evidently well located in this strip. And you have few objects already detected by different techniques. And the goal of TESS will be to add quite a lot of significant objects orbiting bright stars here. So this is really the domain expected for the targets of TESS. So it will be mostly, we can expect to find planets orbiting in the habitable zone, but linked to star, hosted by star, with mass less than 0.5, 0.4 times the mass of the Earth. So it's called, in the jargon of astronomers, M dwarfs. So this, but we have some difficulty, because you start to have a lot of papers in the literature claiming that it will be maybe not so evident that we have habitability linked to short period planet orbiting M dwarfs. You have what are the difficulties? It could be the tidal locking, because if the habitable zone is so close to the star, in fact, you have always the same phase, the same side of the planet looking at the star. So you have this difficulty. You have the problem related with the atmosphere, greenhouse effect, very big. You have the problem of water loss and so on. And it's absolutely far to be sure that M dwarfs are the easiest object to be detected, because the habitable zone is extremely close to the star. But on the long term, I don't know if it's really the good targets. So again, what is expected from tests? Here you have the magnitude of the star observed as function of the radius of the planet detected. All the blue dots are real detection done by Kepler. You see that most of the detection are really correspond to really fine magnitude. And these are the expectations, simulation for the expectation of the test satellite. So you see you have a factor 100. The target expected are a factor 5 magnitude, so factor 100 brighter. So here, but if you are looking really Earth-type planet, so close to a radius of 1 here, and with a distance, let's say, smaller than 30 or 50 parsec, if you do follow-up measurement, you need to have an angular separation large enough to see really the planet. In fact, you almost have no expected object here. These two objects are M dwarfs. So this is really a challenge. Do we have the possibility to detect Earth-type? There are plenty, but the probability of the transit, when you have a very 1 year, 1 AU separation, the probability of the transit is dramatically small, so you cannot dream to detect really objects orbiting bright stars by this technique. And nevertheless, if you trust the theoreticians, the different teams working in the domain, in fact, you have quite a lot of rocky planets expected, hosted by solar-type stars. So, looking the alternative possibility is, do we have the possibility to use the Doppler spectroscopy? Doppler spectroscopy did a lot of progress in the last 20 years. This is 51 peg, about half the mass of Jupiter. And you see the huge increase of the detections, of the planet detection versus the time here. But what is more impressive is the decrease of the mass of this object. Right now, we arrive at the level of 1 Earth mass. But 1 Earth mass for a short period. And it's extremely difficult to find the wobble, the radial velocity wobble for 1 year object. So what is the difficulty? It's not instrumental. I believe we start to know how to get velocity at the level of 2 centimeters per second. We can build this kind of spectrograph. It's not easy, but it's possible. But the difficulty is coming from stars. This is a very small telescope linked to the ARPS instrument we showed before in Canary Island, and just to observe with some special trick the sun, and to consider the sun as a normal star. And you are doing measurement night after night, here, and you see first you have a scatter of about 0.3 meters per second. It's already during one night. But what is worse, that you have a scatter of about more than 1 meter per second on few days. And this is because the velocity of stars, due to the magnetic activity, is not stable. You have a lot of difficulties I will describe later. So in fact, this is really the question. It's the instability of the velocity, apparent velocity of star due to different kind of jitter. Okay, the sun is maybe not the best case because probably we can select kind of stars better with better condition, with lower activity or less important. So what are the difficulties? You have the acoustic modes, stars with 5 minutes, few minutes. You have granulation, several hours. You have spot rotating stars with several days or maybe several weeks. And on the very long term, you have a magnetic cycle like the 11 years of the sun equivalent. So happily, in the domain of habitability, between 6 months and 1.5 years, we don't have any of this physical process. But you see, we are looking at an amplitude of velocity of 8 centimeters per second. So you see, all these problems are absolutely dramatically dangerous. So just an example here. The velocity of one star we have measured, you have a scatter due to the spots, and you have the equivalent of the solar cycle with something like, I don't know, 2,000–3,000 days here, but we have not covered the full cycle. Something like 1/3 of the stars have something similar. All the stars have something similar to the magnetic cycle observed in the sun. So presently people are working a lot to build some diagnostic to see how we can correct this effect and to diminish the influence of this phenomena. But if we carefully select K stars a little bit less massive than the sun, the amplitude of the noise of the jitter is less than for the solar-type stars. And this is a simulation of a 2.5 Earth mass with a period of 200 days. In fact, we have the possibility to detect of this object. Okay, it's 2.5. This object will be in the habitable zone, but it's still a little bit more massive than what we are dreaming. This is a very famous diagram with a habitable zone as a function of the mass of the star, this effective flux received on the surface. And this is claimed to be good candidates for habitability. I will be a little bit more pessimistic. This object here, Kepler-22, is something like with a mass of 12 times the mass of the Earth. The atmosphere of this object will be dramatic and certainly not compatible with the Earth's development. These objects are claimed to be water, ocean planet. Probably, maybe a different problem. All these objects with a large red cross have been shown to be erroneous statistical discussion of the signal. So they don't exist at all, this object. This object here is real. It was discussed a few months ago, but it's 1,400 parsec from us. So, or light years, I don't remember. But so the follow-up studies will be dramatically difficult for that. So, okay, you have some objects on the hot side. Okay, and at the present time, we have no object with mass and radius. So I'm a little bit less optimistic that it's shown in this picture here. But this is an object we have observed with quite a lot of measurement during several years. We have found 3 planets. If you remove the signal of the 3 planets, and you are looking what additional long period of effect exists, and you are binning the measurement by 10 days, 20 days, 30 days. In fact, we already have the possibility to go to 0.2 meter per second, 20 centimeters per second. So we are not too far from the precision we need to detect really by this radiosity technique to Earth-type planet in the habitable zone of solar-type stars. So this is a project in construction in Geneva, but with a large consortium with different countries. It's a huge vacuum spectrograph to be linked to the 8-meter telescope at Paranal, and also with the capability to be linked to the 4 8-meter telescope. It will be, we could receive the photons from an equivalent 16-meter telescope, with the goal of to have, okay, this is vacuum tank in Geneva. So what could be the alternative? What could be the other possibilities? You have a beautiful space mission proposed by ESA. It's a Plateau mission to be launched in 2024, I believe. And okay, in the same spirit of the of the previous transiting experiment like Kepler or Corot, but with different characteristics, and with, for example, the possibility to do asteroseismology for something like 80,000 stars. So if you have a clear asteroseismology signal, you have the possibility to get the precise radius of the star, the age of the star, the mass of the star. So you know exactly what are the stars where you detect a planetary system. The transit, the Plateau mission will provide this evidently signal, photometric transit, and then after we need to do some work on the ground to get the velocity, the mass of the planet. But most of the targets of the Plateau mission will be between 4 and 11, so we'll be in a domain where we have no difficulty to get enough photons to measure the velocity. And in such a case, you have a nice combination of the discovery space of this mission. Here you have the mass versus the semi-major axis, and this is the domain where they can expect detection of signal, and you have quite a lot of, the probability is quite good for orbiting Earth-type planet at 1 year period. So, and obviously if you know that you have a planet with a 1 year period, and then it's a good help to do the measurement, velocity measurement, and to analyze the velocity. I will just finish with an additional future, very important possibility. Here, this is a sketch of a star with a planet orbiting the star. When the planet is behind, you are missing the infrared flux, and you have the possibility to measure the thermal radiation of the star, of the planet, and to measure the temperature of the planet. Once the planet is in front, you have a small filtering of the luminosity of star due to the atmosphere of the planet. So if you compare the spectrum of the star when the planet is behind or in front, you have access to the physics of the planetary atmosphere. So this is called transmitting spectroscopy. Here you need, like, for example, Hubble Space Telescope. Here is a Spitzer's telescope to do this kind of measurement. But you can also do, it was shown recently, you can do the same thing from the ground, at least some limitation. And here, this is one example of the wavelengths emitted, measured during the transit spectroscopy measurement, is the ratio of flux, and you see this black square as a real observation done in the close infrared, near infrared. Long infrared is not so nice, and you have several curves corresponding to different kind of composition of the atmosphere. So it's still not very impressive, and this is the present situation. But some of them was done from the ground, a lot of this measurement, and with the arrival of huge new telescope, for example, you have the project of the 30 or 39 meter telescope, for example, in north of Chile, the ELT telescope. So you need a lot of photons because the effect of the atmosphere of the planet is so small that you need to accumulate a lot of photons to have a significant signal when you do the subtraction of the two signals. So I'm sure that in the last 10 or 20 years, we will have a dramatic improvement of the physics of the atmosphere of planet due to this kind of techniques. Thank you.
Thank you very much for giving us insight into these exciting discoveries that are being made here. Are there any questions? Yes, please. Please use the microphone.
I'm an atmospheric scientist, so it's probably a silly question. The concept of habitability of a planet is based on having water in liquid phase. What about the possibility to have different chemical mixture as ammonia, as a possibility for habitability, and which are the implications on the classification of the habitability on exoplanets?
Yes, this is certainly not the full possibilities of life possibility. If Athena Koustanis would be here, she will claim that we have other possibilities like this. And for example, also you have all the possibility of underground ocean, like in Europa or in other place. And so this is only for the expectation of life biased of the carbon based on water and on the surface, because it's underground, it's very difficult for extrasolar planet. I don't see any possibility to detect life. Already, if life exists on the surface of the planet, it will not be very easy to detect life at distance. You need to have a very, very good analysis of the planetary spectrum to detect some biomarkers and so on. So I fully understand, agree with this statement that this is not the full, this is not the full possibilities of life, existence of life condition.
Other questions? Well, should we then thank Michel Major once again for this great overview of the search for exoplanets. Thanks very much.
Thank you.